Welcome to Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. We are continuing in our lectures now with more examples of equilibrium analysis. This is hopefully going to sound very repetitive because hopefully you'll start to see trends and the same principles more or less being applied over and over again, but some problems may at the surface kind of tend to look totally different, and it's very easy to go, I have no idea how to apply these principles that I already know, but if you get used to it, you start to realize that really they're all pretty much the same, and you just kind of start going through a system of analyzing them. So you're going to get quite a few examples to kind of get you used to seeing what you've learned everywhere, because that's exactly what you're going to need to do in the professional world. Okay, so this is I call it the dumpster problem, and pretty much every statics class gets something like this, so it's pretty classic. So we've got a load. This is like a big box right here. It's a big rectangular kind of bin or something. And this is a 2D problem, so we're going to assume that whatever structure and geometry goes in and out of the paper is the same. So we really only need to look at forces in the X and the Y and moments in the K, the Z direction. So all of our moments are going to be coming out of the paper. So we've got a 2D system. And we've got some kind of hydraulic cylinder here that can push only in the direction that it's oriented, and that's fixed because we're told that the point of application is exactly 3 feet from this bottom surface, so that along with this measurement is going to define our angle here. And we're told that the weight of the bed and the contents, so this is the bed, this big box, that's the bed, and it's got something in it, and it's uniformly distributed more or less, and so it's got a center of mass at point C, and we're given dimensions where that is, 6 feet, so it's right in the middle from the standpoint of the box length, and it's 1 foot down from the top, so maybe a little bit top heavy. And hydraulic cylinder goes between points B here where it contacts the bed and A, some here down on the floor, and we're given some other dimensions so we can get lines of force and offsets for moment. And we want to know what the force that has to be applied by the hydraulic cylinder to keep this load, this bed and contents weight load, in static equilibrium. And there is we can assume that there's a pin at the bottom and a reaction force that the surface makes. So this can't go skidding out. So it's basically a point D. There's no moment that can be applied, but there's like a hinge force there. Okay, so we need to know how strong that hydraulic cylinder has to be. So we would maybe be sizing the hydraulic cylinder, knowing what kind of force it has to apply. That would be a major purchasing spec if we were to buy it or specify it. So we would need to solve a statics problem first to know what we need to buy. Okay, so we have a variety of FBDs that we can draw. We can, if we were really concerned about the reaction at the surface down here, we might want to draw an FBD of the entire cylinder and bed, but we're really only concerned with the force between the two bodies. So let's start looking at FBDs of the bed and the cylinder separately. So we're going to start with an FBD of the bed, and that's very likely going to give us quite a bit of the information we need. And what you'll find on this particular problem is the geometry is a bit trickier than you would think. So I've actually worked this using some vector algebra just so that I don't have to worry about properly envisioning all of the angles and offsets. So this is an example of vector algebra being used in a real problem alongside geometry. So I slapped a coordinate axis on just to keep my signs straight, And because I know I'm going to be doing some cross products, this is really important, so I know how to set up radii and forces in their I hat, j hat component directions. So here's my FBD. I've replicated all of the relevant dimensions that I need to position forces. So I have a force AB that is what I'm ultimately going to solve for. It's at an angle theta, which I can find from taking the a tan of 3/6. I have the weight force that's vertically downward. We were told it's 1,200 pounds, and it's acting at this point C, which is in an odd place. That's all referenced to kind of the top of the bed. I can use the other dimensions, 10 feet here, and the total bed thickness, which I think we have, which is 3 feet, that I've obscured with my scribblings, but the total bed is 3 feet high, so I can use some of those to end up getting the angle theta, other dimensions, so I can get that. So I'll start by writing expressions just in terms of degrees for the different angles. So phi is 36.9 degrees, and phi is 26.6 degrees, and theta is 36.9. 26.6 and 36.9. So geometry close-up. If we're to look at the bottom surface of this bed and all the different angles we make, and we wanted to drop, say, a perpendicular from it, we can use that to get pretty much all the angular relationships through the bottom of the bed. So we knew what theta was, and we knew what phi was. We can use various right triangles to walk our way through all of the angles that might apply to this line of force that we might need. So we've got those in our hip pocket. So we can also use dimensions and right triangles to project our line of action of our force up into the bed, and use that to get a moment for our weight. So this section here is a little special treatment, getting the moment of the 200-pound weight about point D. And I'm not going to walk through every single step of everything, but basically some of the forces in the X and the Y are pretty easy. We're going to have some of the forces in the Y is going to include the weight, the vertical component of AB, and the reaction at D sub Y down at that bottom hinge corner. And the sum of the forces in the X are going to include the horizontal component of AB balanced by the horizontal component of D, whatever's pushing back, and those are going to be equal. So that's pretty easy. What's really going to give us the answer we need is moment. So we have two forces that can basically apply a moment around point D, and I've chosen point D to be the point around which I will sum moments, because then D sub X and D sub Y kind of disappear. I don't have to consider them. I already know the 1,200 pounds. I can find a radius or some kind of perpendicular to that the length of a perpendicular to that 1,200 pounds from the geometry if I try hard enough, which means that force AB, if I can get a radius from point D to it through the geometry of the problem's dimensions, that will give me AB in one equation. So the thing that I need to know can be solved just by the sum of the moments about point D. Then I can take that, plug it back in, and get these point D reaction forces. So that's the strategy. And I can do all of this with just the FBD of the bed. So the real challenge with this is just getting the geometry of the angles of lines of force and the actual radial offsets if we want to find a point where the line of force is perpendicular, so we don't have to consider that sine theta. So this is one using this assembly of triangles, And this one schematic, this is an example of how you can do this geometrically. And this is basically just using some trig and basic geometry to find our perpendicular offset distance, or at least a line with a known angle, so we can get a perpendicular offset. So this ends up being our force, and this distance m from the hinge times cosine of theta, which is this angle here, ends up giving us our perpendicular distance of the force. And I won't walk through all of the geometry. You can do that if you would like to. But it was, took some careful considering of the problem's geometry to do that. Okay, so having gone through that and gotten that moment, it was basically simple to solve for AB. So here's our sum of the moments equation. Had to be 0 to keep it in static equilibrium, of course. Here's the contribution of the weight coming from up here, and then we were able to use some trig to get our total distance, and then taking the sine of gamma up here. So this was 5 feet we were able to determine, and so by using the sine of gamma, that gave us this perpendicular between our force and a line going through D. So a lot of geometry, lots of tricky geometry to calculate moments here that I didn't totally step through, but you can certainly do that given the geometry of the problem. Okay, so obviously I was unimpressed with how much geometry I had to do, so I decided, let's see if there is a better way to do that. And so I decided to look at calculating moments directly with a cross product, because I thought it might be easier to get radii and just let the cross product take care of more of the geometry for me. So I started with the moment of the weight about point D. So I know the weight is applied here at point C, and I can draw a radius vector RDC up to point C from the hinge point at B, and then I can cross it into the weight. So really now all I need to know is something about the x and y components of this point R. Okay, the angles are a little tough, but all I need to know is this length and that length in order to get the x and y components of R. And of course it's going to have a negative x component and a positive y component, RDC. So unfortunately I still had to do a little bit of geometry to find the exact location of point C relative to point D, because all of our dimensions are relative to corners of the box. But I was able to get the x component is negative 3.6 feet and the y component was 5.2 feet. So there's my radius vector from point D to the point of application of the weight at the center of mass. So here's my weight vector, negative 1200 newtons. Newtons or pounds? Pounds. This is a British system. So 1200 pounds in the J, and here's my radius vector, cross them together and get 4,320 foot-pounds k hat. And the very fact that this came out automatically as a k hat and a positive k hat is a check in and of itself, because we know that the only moments that we should be producing are going to be in the k hat or negative k hat direction. And furthermore, I know from just observation of the radius and the orientation of that weight vector that it should be the positive k hat by the right hand rule. So I have some confidence in that. Okay, a little bit of checking. Okay, the next job is to look at the moment that I would get around point D from force AB. So I had a vector D to C, and now I need to get the vector from D to B, which is a little bit simpler. So I'm going to be looking at, from point D, we have a horizontal. So I basically need to know this distance and that distance. I'm going to have a radius D to B along here. So it's following the bottom length. So it has an orientation along the base of the bed, and I just need to know how far to go. And I can maybe look back up at the original problem and get some information. I've got 4 feet in one, 3 feet in the other direction, so that I can get fairly easily from the original problem. So I have -4 feet horizontal and 3 feet vertical coming straight off of the original schematic. So I can cross that into my unknown force, and first I have to express my force, without any of its own length, because I have to get its direction. So I actually had to take out part of the length of my force vector, expressing it just as a unit direction with some magnitude, because that's what I really want. So I've done that, and so this is an example of using a unit vector directly to express a force where I know the direction of the force but I don't know its magnitude. So I had to divide out effectively the length that I was using to express its orientation. So I expressed the orientation of vector AB relative to point D, and then took that length back out, and then just multiplied by the force magnitude. Okay, did that, took the cross product, and got -10 feet in the k-hat direction. Multiply back by my components of the force that I did up here. Set that equal, and which is this part that I had divided out. And so I'm going to say, okay, this is effectively the moment, the magnitude of the moment, big circles here, due to the hydraulic cylinder. So here's my magnitude. That's going to have to be equal to the moment due to the weight. And so I just do some algebra, isolate AB, and it ends up being 966 pounds. So that was 2 different methods for solving a fairly simple statics problem with some reasonably complicated geometry. And if you look at the answer that we got in the purely geometric case, it's pretty close. So that gives some confidence that we were doing things right. Okay, so you can step back through the geometry, lots and lots of right triangles. So right triangles are definitely your friend in finding dimensions and lines of action. You don't have to use vector algebra in a lot of these, but there are times when it can be helpful, like I showed, when you have easy ways to determine coordinate points. Okay, so we have another example. This time we have curved members. So someone has 2 half or quarter circles. So each component is a quarter circle. So if you're going to draw a point, at the theoretical center, that would be 90 degrees, 90 degrees to the middles of those. Get rid of our scribblings. Okay. And they're equal radius. So, and even though it's not necessarily drawn this way, with the equal radii and this point being the same here, these 2 points are actually on the same level. There's just a, it's difficult to hand sketch circles. So they're connected by pin connections everywhere. So we can apply a force in the x and the y at A, and a force in the x and the y at B, and we can swivel around point D, and this pin can yank in whatever direction, but it can't apply a moment. And somebody wants to know, what are the reactions at points A and B if the entire structure is subjected to a couple equal to 60 foot-pounds? And it's just shown here. It doesn't really matter where it's applied, because remember, it doesn't matter where couples are applied. The whole thing is twisting like this. So there's a 60 foot-pound generalized torque being applied, and so the forces here and here, whatever direction they end up being, are the only things that can oppose it. So we were being asked, okay, what are those forces? Okay, something important to note: what is and what is not a two-force member? And that's really important for getting a solution. So remember, a two-force member is anything which any body that is subjected to two forces and nothing else. And if it is, then we know that those two forces are equal, opposite, and collinear. So we'll start with member AD. It obviously has forces applied at A and B, and it has a couple moment. So the moment is being applied over there. So in this sense, the location at which the moment is being applied is important. It wouldn't be important for the whole body, so it is important that in this case it's applied over there, which makes DB a two-force member. So things can move at the hinge. So generally, the point of application of a couple isn't important. This time it actually is, because we have something that doesn't necessarily transmit moment. So hinge D. So the moment is everywhere similar all over this member, and then this couple moment would be transmitted by forces applied at pin D across D to B. Okay. Apologies for the confusion. So that's kind of the key to getting our additional piece of information that we need to solve the problem. So let's start with an FBD of just our member BD, and drawing it. So this is a circle. So if we want to draw a line that connects these two, basically we've got what's effectively a square. Our geometry tells us that the line connecting the 2 points on which the forces are collinear is going to be a 45-degree angle to vertical. So we now know the lines of action of the forces at D and at B, because the reaction forces at point B, the support reactions, are only going to be reacting to whatever the member places on them, and the same thing up at D. So if we do an FBD of pin D, this force of member BD on the pin is going to be reacted against by this. So we now know an important piece of information. Okay, so we're going to allow the member BD to react through the pin and apply force FD to the left-hand member. Okay, so we now know the force of the pin up here at D on our left-hand member. So we know what this is, or at least we don't know what it is, excuse me. We know the direction that it's pointing, which is half the battle. We know half of what it is. We don't know its magnitude, but we do know its direction. So we need the magnitude of F sub D, and then we need the magnitude of A sub X and A sub Y, and we are given a couple. Now this time, unlike the whole body that has a non-moment supporting pin in the middle, now we have a rigid body. So in the case of this body, this 60 foot-pounds would be the same down here, in here, and up here. Okay, so there's where rigidity becomes important in allowing us to apply a couple moment everywhere along a body. Okay, so we should have three reactions, or excuse me, three unknowns and three equations that we can write equations around and solve for. So here's our unknowns we just went through, and so it's statically determinate. We can find all the forces. So we can write the sum of the forces in the x. So we have F sub D sine 45. Cosine wouldn't really matter in this case, but we'll take it as sine 45 going in the negative direction, and then that's being opposed by, well, basically it will end up being opposed by A sub x, which we're quickly going to find is going the way opposite drawn. And then some of the forces in the y, we have A sub y, and of course we have the y component of F sub D, which is the same as its x component because we have a 45-degree angle. And then of course we have moment. So we have to find how are we going to resist this moment. And we can wisely take our moment around point A and immediately get a solution for F sub B. So the moment due to F sub D, and this should actually say D because I believe that's what's up at the top. This should be a D, is basically going to have to be equal to the applied moment. So if we use the right hand rule, this 60 foot-pounds is actually pointing in the negative k hat direction, and we can use a little bit of geometry, the radius, the r cross f, so we have a radius from A to the point of application of point D, and this is actually forming quite handily a right angle. So all we need to know is the length of this. We have 2 feet here, so basically we can use cosine relationship or sine. Divide by cosine to get the hypotenuse. We could also do Pythagorean because we know that this is 2 feet over here. 2 feet. A line method for feet. And so this is the magnitude of our radius vector. We know it's at a right angle, so our sine theta is 0 for our cross product for moment, and so we can solve directly for our F sub D, which is the same as F sub B from the two-force member. Plug that back in here, and get our reaction forces. So it turns out that A sub y was correct in the direction shown, so the support is yanking down and is pushing to the right, and the support at the pin is going to be pushing in the direction shown. It ended up being positive, so it's actually going to be pushing up and to the left on this member, on our left-hand member. And so a question to consider is, do the support reactions themselves form a couple? And we can actually get that by going back up to the top and realizing that there are no applied forces, just an applied couple or an applied moment. So there are no external forces to balance a net force coming from the supports. So the supports have to only themselves apply a moment that opposes the 60 foot-pounds. So in reality, the sum of the forces at A and plus the sum of the forces at B all have to cancel out. So in reality, A and B will function. The net combination of the support reactions will function as a couple in this case. Okay. The next couple of pages is actually a theoretical proof of what we've been doing with connecting forces being equal and opposite. And it's if you like mathematical proofs and it helps you understand things, go ahead and step through through it. I'm not going to step through everything. It is very theoretical, but it basically gives an independent equation of equilibrium argument for applying equal and opposite forces collinear at contact points between bodies. And so it's just another way of basically getting to what we just applied Newton's third law to get. So it's an interesting proof. I'm not going to go through it, but if you like proofs, great. Okay, and we will skip ahead to, we have one more example with pulleys. So one more example in this section. Okay, so we are given a pulley and a weight system shown. And so if you've ever done these kind of problems in physics, applying good equations of equilibrium is a really simple way of solving these crazy pulley and chain systems. You might want to ask, where would you ever use this? Any kind of lifting operation in a manufacturing or construction facility is going to involve calculations like this. So if you're buying a new crane, or you're basically determining if your lifting system in-house can handle a given load, move a piece of equipment, you might be going through calculations like this to determine if you're capable of making a move in-house or using your crane for a given project. And that's done all the time. So someone wants to find F in this case, and this is not a force, this is just an arrow indicating that you're looking at the rope. So someone wants to know, how hard do they have to pull on this rope in terms of W2 and W1 to keep everything in static equilibrium? And somebody also wants us to describe, do W1 and W2 have to have a particular relationship between them, which will probably turn out they do, but we'll determine it one way or another. So we're going to look at applying different FBDs to this and get an idea of which ones will help us get what we want to know. And just for reference, this fuzzy thick line is like some kind of chain that's just connecting the center of this pulley P2 directly with the weight W1, and then the thin line is a rope that goes from the center of pulley P1, goes under pulley P2, over pulley P3, and then we're going to apply a force to it. Okay, so let's start with an FBD of the whole system. And I got a big blob with pulleys and chains and weights in it. So we know that the force that we're pulling downward on the rope we're pulling straight down. So we've got F going downward, we have weight 2 going downward, weight 1 going downward, and we have the two support reactions. Okay, we can't write moment equations, we don't have dimensions. We could if we had dimensions, but no one gave them to us. So this is, while it's theoretically correct, it didn't get us very far. So next we're gonna cut apart pulley P2, just pulley P2. We're not gonna include the weight. So just everything in here. Okay. So if we look at P2, we've got a rope twice. We've got the chain once, and we have weight coming down. Okay, so we know that the tension in our continuous rope, there's no friction in this system, so the tension in the rope is the same everywhere. So we have the rope force once, twice, and then we have the chain once, whatever that is. And then we have weight 2 connected with it. We can go backwards. We've kind of inserted something from another FBD. We know that the force upward, I'll scroll back and zoom in a bit and maybe erase some scribblings. I've not rigorously done something to erase some scribblings. We'll walk through the whys of how we got everything. Okay. So our chain is connected to weight 1. It goes over our frictionless pulley and is connected to P2. So it has a continuous tension in this chain that has to be equal to weight 1. if I were to do let's do a quick impromptu FBD of weight 1, we'd find that it has a downward force due to its weight, and then it has an upward force due to the chain. It's in static equilibrium, it's just sitting there. So that immediately says that this chain has a tension in it, because it's the tension in the chain that's keeping weight 1, the literal block of weight 1, from falling down. So that tension is equal to weight 1. So the tension in this chain is equal to W1. So we replicated that at its other end that connects to the center of pulley P2. So we can write an FBD for pulley 2 in terms of F and W1 and W2. So no moments, no forces in the X's, is all forces in the Y. Very, very simple. So 2 times F plus F1 in the chain minus F2 equals 0. So this immediately gives us our force in terms of the weights, which was basically something that we were asked for. So it was a single FBD that gave it to us, because we wanted F in terms of weight of the two weights. It's important. Now, why would you need to know that? Say your weights for 2 things you needed to lift, and say you were sizing the rope that you were going to pull. You had a big winch, you had plenty of torque, you could pull it with as much force as you wanted, but you needed to know what size of rope you needed, or cable. Maybe you needed a steel cable. So with this, now you can size that, and it turns out to be kind of non-intuitive. You're not necessarily just adding them together. So mechanical advantage. So next we want to think about, okay, we were asked, what can we say? We were asked to know what relationship can we say there is between the two weights to keep everything in static equilibrium. Well, this turns out to be a property of cables. So F has to always be positive in the case of a flexible type of tension member. It is a tension member. You can't push it. It can't go into compression. So the relationship between W1 and W2 is whatever it takes to keep this expression positive. Well, for that to be true, all you have to say is W2 always has to be greater than W1. So that's the answer to the second. F equals the difference between W2 and W1 divided by 2, and W2's got to be greater than W1, because you can't push a rope. So that was this problem. So basically just a single FBD, all our forces in the vertical, that was all it took. Now we could have FBD'd every pulley, and we can get some other relationships. We can FBD this one, we can FBD pulley 3, and we can use these for checks, in fact. So we can put in a relationship that we got for F into any one of these other FBDs and check ourselves. So that's another nice thing about using multiple FBDs. So that is it for this lecture. Lots of examples, lots of geometry, different options for dealing with your geometry. You can either do it directly, or you can do it with the assistance of some vector algebra and a little bit less geometry. But in every case, no matter what you do, what you're looking for is an accurate expression for the magnitude and direction of forces, and a way to tally up their components in x and y and maybe z directions, and a way to calculate moment. And in the case of things like two-force members, those give you critical additional relationships that you need so that you have enough equations to match your unknowns. So we'll have 1 or 2 more general recordings, and then this will be followed by a sequence of example-only recordings that should be all present in your Canvas module on equilibrium analysis.